Can't you see I don't have? I do it for I don't have.
Okay, thanks, Sarah. So my name's Suzy Morgan. I'm a technical team manager at NNL Windscale, and I'm going to talk to you today a little bit about working with highly active materials. So my question to you is, if you wanted to look inside a nuclear reactor core and see if it had been operating effectively and efficiently and safely, how would you do that? And as well as that, if you wanted to see if that fuel could be safely stored for generations to come, where do you start? How can you really see something that can't necessarily be seen? So, in order to start answering that, we can perhaps look at something like this. We can take a little sample like this of our nuclear material and something like the digital camera that's in your phone. And we can use that to help us understand reactor performance and efficiency. And in addition to that, what we really need in a situation like this, operators that we know can handle this material and can do it easily and safely. Okay. So what roughly is it that we want to look at? Well, in the UK, we've got nuclear fuel, which is mainly oxide fuel. And this is comprised of many component materials, all of which interact and have an effect on the efficiency of our reactors and the way they operate. Roughly translated, this means that it's how much power is available for you to boil the kettle or perhaps switch the light on a dark evening. So what are these component materials that have such an effect on our reactor performance? Okay, so as you can see here, we've got many materials that go into making the reactor fuel. Broadly speaking, we have nuclear fuel, and fission goes on in those fuel pellets. That generates heat. That's then transferred through our stainless steel, which encases our pellets, into a carbon dioxide gas coolant, which is then transferred on through our turbines and generators to produce power. This is an advanced gas-cooled nuclear reactor and is the most common type of nuclear reactor in the UK today. So, the component materials within this nuclear fuel, what are they if we look at them in a little bit more detail? Well, as you can see in this image on the left, we have fuel pellets. We have over 60 of these, and these make up one 1 meter in length fuel pin. Okay? So, 36 of these fuel pins make up one single fuel element. In addition to that, 8 fuel elements make up one fuel stringer. And then we have tens of fuel stringers making up one reactor core. And to put that into some context, we have 14 operational AGR reactors in the UK today. That's a lot of nuclear material to study. So what else have we got to consider in this equation? Well, we've just said it's a nuclear reactor. We need to look at radiation. So what do we know about radiation? We've got such large quantities of material, and we know that in large quantities or high doses, radiation can make material difficult to handle and difficult to get close to. So what can we do? Well, we can build a facility so that we can shield it. And this is what's known as a hot cell. And traditionally, where we handle most of our highly active materials in large quantities. It's several meters of shielding, usually lead, concrete, glass, as you can see here, so you can see into the hot cell. If you take your material, which is, let's say, around here, you as the operator looking at that material might be standing around here to actually look at it. Well, that's a long way away. And you need to pick the material up, you need to turn it around, and you need to be able to see the back of it in order to do that examination. So what is it that we can use to do this? Well, we can take remotely manipulated arms that are built into the hot cell with jaws on the end, similar to these. And these jaws we use to pick up our material and handle it so we can look at it and assess the performance. So that's it, right? We've got our material in a place where we can handle it, we can see it, we can move it around, and we can look at it. But actually, we really need to see it in a bit more detail. Ideally, I'd like a microscope so that I can look at my material and see the structures and see them and really understand the microstructures in my material. So, I take my microscope, maybe my digital camera, something similar to what we were talking about before, put it in my hot cell, connect it up with several meters of cable because my material is there and I'm here, switch it on. This is really good. I can start to look at what's going on inside the reactor and inside the material. Switch it on. Might get something like this. As you can see, this is not a kind of image that tells me anything about the material I'm looking at. This is the kind of image you might expect to get if you put large quantities of nuclear material near, let's say, a digital camera sensor. And it's because of the way that radiation affects our standard components in a lot of our advanced scientific instruments. So, we've got something that we should be able to look at our material with, and we've got our material. But we can't actually see it because of these problems. What can we do next? We can take our material and we can take our equipment. And then we need to work out how to build it so that it works in this environment. We really need an established, a really good supply chain and someone that understands the demanding environment that we're having to work in behind several meters of lead and concrete and glass shielding with lots of radiation. I need a really flexible supplier, one that is willing to take standard off-the-shelf equipment, maybe rip it apart, something they've spent years designing, and redesign it all again for me. And then I need to be able to take out all the radiation-sensitive components, put the equipment back together, and have a working piece of equipment that I can put in my hot cell with my material. And at the end of all this, I need to be able to trust the results I'm getting from my equipment. And I need to be able to trust the results in an environment that doesn't adhere to any internationally accepted standards. Because of this, I need to build the standards so that I can take my measurements from my material and get some useful information at the end of the day. And on top of it all, I need to do this day in, day out. Okay, so we've established that we need scientists and technicians who know what they want to look at, and that we need a supplier and a supply chain that's flexible and can work with our needs. So what can we do to make it easier for us to work with? Well, we can take our material and we can make it smaller. So we can take our 1 meter long fuel pin and we can take a chunk out of it and make it like this. What that does is reduce the amount of time that our sensitive components are exposed to radiation. So if you take your microscope again, it'll be something like the glass lenses or the digital camera in the microscope. Those glass lenses actually darken with time and exposure to radiation. And so as they darken, they reduce in visibility until eventually you can't see anything through them at all anymore. And I'm reliably informed that visibility is an essential quality in an optical microscope, and you really need to be able to see through them in order to do your examination. So, we've got our microscope here. We've pulled out everything we can, and we've put it back together. Okay? So, the microscope you see here is actually the microscope you see here in red, and it's been modified. We need to calibrate it, and to do this, we need to go in, I need to go in dressed in a suit, a respirator, shoes, 3 pairs of gloves, and calibrate it so I know my measurements are accurate. That's quite hard work on a day-to-day basis. And finally, 18 months after I've done this, I can start looking at these, my samples. So, I need to standardize my material as well. You can see here I've got a whole variety of different materials that I want to look at. Actually, it'd be much better if I had them in one single format. So I've got that. I want to look inside my nuclear material. I can see here microstructures and features that tell me that this material has been operating just as I expect it to in the reactor, and shows me the different temperatures that the reactor is operating at. As well as that, I can look inside the material and I can see that we've got features like this carbon deposit, which can be put down on the pin surface as a result of the coolant running around our reactor, and can actually inhibit the heat transfer between our fuel pellet and our carbon dioxide coolant. It acts like a duvet around the pin, if you will. Okay, so I can assess my reactor performance. I can make much smaller samples. I can take them out of the cell. I can assess how easily these fuel pins can be stored for long periods of time. If you think about that, I'm assessing performance, and I'm assessing performance during long-term storage. And that's pretty impressive from where we started, with a material that we couldn't actually handle and microstructures that we couldn't actually see. So, I'd just like you to take a moment to think about this and think about all the work that goes on behind the scenes on a day-to-day basis to keep energy flowing every time you switch on a light or boil the kettle, and think about the really unique facility that NNL has and people that do this difficult and complex job day in and day out, just as you might switch on a light day in, day out. Okay, thank you.